Thank you for your patience, everybody. And thank you for this invitation at the workshop to Michael. This talk is well placed and is in continuity with the lecture that Andreas gave earlier, and somehow with Tim's as well. This focuses on proposing an empirical methodology to build damage functions to estimate the risk of growing climate uncertainty on different sectors of the economy. So here, the content of the talk first will bring you through what is the state of the art of these famous damage functions that Tim was talking to us about, before presenting the methodology, the more data-driven weather within climate methodology that we've developed, and showing how it can be applied to design optimum strategies to manage that risk that is rising from the growing uncertainties of the climate system. So how do we optimally invest in reducing risk or in transferring risk, for instance? And lastly, we will present, I'll present one empirical application of this methodology in managing risk in agricultural markets, and in particular an application to financial inclusion in sub-Saharan Africa. So damage functions have been used in very high-profile studies, such as the Stern review on climate change, or in the DICE model of Nordhaus that Tim just mentioned. So what happens in these frameworks is to take a production function. In this case, this is a very mainstream model, the Cobb-Douglas production function, where the production here a function of technical progress, of capital, and labor, for instance, is eroded here by two factors. First, how much does one invest in mitigating, reducing the carbon emissions, and how much growing climate uncertainty is eroding the production. So what we're interested in this presentation is in this parameter alpha t, which is the damage function. What is a nice paper by Diaz and Moore in Nature Climate Change unpacks what is contained in this alpha, all the different processes that the damage function contains. So what alpha contains, the damage function, is first a variation in some climate driver that generates a physical damage, a physical loss, that then generates an impact on a different, leads to a different equilibrium state in a given sector of the economy. It has welfare impacts as well. One can decide to invest in adaptation, so that will influence how much damage that physical, the energy sector, the agriculture, transport, whatever it is, will suffer, but it will also increase the cost of these damages. So this diagram that you can find a little bit more aesthetic way in the very nice Nature Climate Change publication by Diaz and Moore is everything that is contained in this damage function. Different studies have modeled this damage function in various ways. Here, focusing on this one by in the Stern review on climate change. This is the same damage function used in the DICE model of Nordhaus. And you see that the only thing that varies between Stern and Nordhaus is the quadratic function here. So in the case of Stern, you have it's a stochastic parameter that varies between 1 and 3, and Nordhaus decides that it's quadratic. There's various variations of this damage function that have been proposed in a number of other studies. It's becoming a richer and richer literature, where team is contributing, of course, by embedding the impacts of the presence of tipping points. One feature that is common amongst all these climate damage functions is that you see it is all a function of the globally average surface temperature, here capital T. So this is a common factor amongst all the damage functions, and this is exactly what we are going to try to unpack in building empirical damage functions that are that reflect, in fact, the true damage in different sectors of the economy. An important feature of these damage functions is that they don't allow for fat tails. So you see, as the temperature increases, you have an exponentially decreasing erosion of the economy until it reaches zero. So what we are trying here to do is to go from the ground up, taking a complementary approach to what economists have been using in computing damage functions, and really taking a more data-driven, or I'd rather say a data assimilation-based approach, couple this with the climate and see how can we characterize the damages that growing climate uncertainty is going to cause on different sectors of the economy. So to do this, what we use is a semi-supervised. We start by here. IJ is different latitude, longitude coordinates. If you place yourself anywhere in the globe, this is what IJ means. Z is any feature of hydrometeorological variability that can affect an economic sector. So in Wall Street or in the city, they have been quite used to develop original weather indices, and there's a market, the market of weather derivatives, for instance, that has been quite active in developing these energy derivatives where critical temperatures are assessed, and where that act as with a threshold effect, where above a given temperature demand falls, or demand or below, if winter temperature surpasses a given threshold, then therefore energy demand falls, and energy utilities insure themselves against such shortfalls in revenue through the energy derivatives market. But so here this Z can be anything, right? If you're talking about agriculture, agriculture will be the application here that we that we'll present in these slides. Agriculture is much more complicated because there's an interaction of rainfall, of temperature, and many other variables, meteorological variables. So here what we do essentially is build a statistical universe of different features of hydrometeorological variability that will affect the production at a given point in space. And by implementing a random forest, identify what feature of hydrometeorological variability is affecting production in a given site. Here is, this is how we go from the Zs to the Ws. W here in the rest of the presentation is what we call the optimum weather index at location IJ and in a given technological scenario. So we are looking at how weather volatility is eroding or is driving economic production in a given site, subject to different technological scenarios. U here. So here, for those who are interested, I can go back to this. This is the algorithm of random forest that was developed by Leo Breiman in 2001. where we use random forest to quantify the importance of different all correlated variables. So the reason why random forest is used is to uncorrelate different collinear variables. So in the case of agriculture, for instance, you can think in a given site, is it the cumulative precipitation from May 1st to July 15th, or from May 15th to July 2nd, and so on. And you can build a statistical universe of collinear variables like that, that you will decorrelate and find the weather index with the highest explanatory value of losses. So here in a statistical universe, so this is a paper that we published with Michael and co-authors 3 years back, 3 or 4 years back. In your statistical universe of roughly 150 different weather indices, here you achieve giving them an importance score, and you will use the most important weather, the weather index with the most important importance score to characterize the uncertainty and the risk that the economic sector is at. So what we're doing in addition to taking globally averaged temperature is also putting a probability distribution around optimum weather indices to quantify the risk of loss and impact in using historical data. So this is here. This is simulations done in China. Here I'm just plotting 2 weather indices. The optimum weather index is here the blue dotted line. And here the black dotted line is an observed crop yield. So this is the observed crop yield in a particular location in northeast China. And you observe what how the optimum weather index built only using rainfall, daily rainfall data, how it matches the physical production of the crop. So here you see a mismatch, and of course, not only rainfall drives agricultural production, but there's a number of other variables. And this work was done in collaboration with crop scientists and crop modelers to provide observed crop yield data. An example in a couple of other pixels, locations in northeast China, in the province of Shandong, that you will see later. And then we achieved these results. Here you have a map of Shandong province where you have optimum weather indices that are illustrated by different colors, and the different colors going from green going through yellow, red, and blue means at what period of the crop growth the weather index is centered. Does here, if you see it's green, it means that precipitation variability drives yields if it occurs at the beginning of the crop season. If it's blue, it's because it's rather at the end, and red rather in the middle. So essentially, we are exploring the statistical universe of weather variability and see how it affects the production. So here in agriculture, you could think of any other sector. These are temperature indices, so we are looking in a bivariate world. These convoluted equations look much more complicated than what they are. This is just to point that unlike the framework used by Stern and Nordhaus and the majority of economists here, we are allowing for the probability distributions of these weather indices to be heavy-tailed or not. So this function here is a smooth function that is modeling the transition between an exponential probability distribution family function, in this case a gamma function, with a generalized Pareto distribution, to allow for the possibility that we may have fat tails in our distributions. So here, this is the probability distribution of an index in location ij. And here we characterize the loss function using a non-parametric function. And right, so before going that, so I'll go 2 slides back, but essentially, so at the moment what I explained to you is that we have for each pixel the probability distribution of an index and its loss function. Then I'll go 2 slides back to show you what is there 2 probability distributions here. To project the losses in different climate scenarios, and when it comes to vulnerability to precipitation, we cannot take, of course, climate model outputs at face value. Climate models are cutting the atmosphere and the oceans in cubes of roughly 50 kilometers at best, and the cloud measures 2 kilometers. So if you look at regions that are poorly calibrated, such as Africa, such as regions of Western China, you cannot, roughly half the climate models are telling you that the total average precipitation is going to increase, and half the climate models tell you that it's going to decrease. So in order to project the probability distributions of these optimum weather indices in different climate models, we model them conditionally on some large-scale climate driver, a climate process that is driving here regional weather patterns, which are in this case latent variables that drive conditionally these probability distributions of the weather indices. And this is done using a hidden Markov model framework that is made non-homogeneous by here making the weather. So these latent variables, you can feel them like weather regimes or weather patterns over a given region. So here, a cold and wet winter, or a cold and dry winter, for instance. So if you have two weather regimes, which are going to be influenced by the, here in Europe, for instance, by the North Atlantic Oscillation Index. If you are in China, like we did here, it's going to be, you're going to be interested in the monsoon, and therefore the contrast of temperature between the landmass and the ocean. So this is why we used in this toy model an ENSO, an El Niño Southern Oscillation, which is the sea surface temperature anomaly over a chunk of the Pacific. 5 minutes. All right. So I'll accelerate drastically. This is why we have two probability distributions here, and we make the weighted sum of these probability distributions that is going to vary in different climate scenarios, of course. As the climate warms, we are going to be extracting from the climate models the variables that are most reliably modeled, which are more spatially averageable variables like sea surface temperature. Moving fast forward, I'm going to skip this part. Once we have these probability distributions in all the pixels and in different climate scenarios, you can have the probability of loss in each of these pixels. You aggregate that for a region of any scale, and you have a loss function. So instead of having damage functions, here we have probabilistic damage functions, where we are estimating the loss to the economy at different levels of probability, or here as illustrated in return periods. So here, these loss functions are used as an input variable in an economic model to disrupt the supply in an economic system, and therefore assess how much loss in the whole economy we are going to have if we have a 1 in 150 years event, for instance. in a given technological scenario. So here red is irrigation, black business as usual, and yellow you put a crop variety that is not adapted to that region. So I'm going to skip that part. This is here we built a model with Enrico where we are optimizing from the social planner's perspective how much do we invest in reducing risk versus how much should we invest in transferring the risk to the financial markets. So how much do you invest in insuring yourself or in reducing risk? And here by maximizing a utility function where we embed a premium that you pay, the payout that you receive, and here that weather index that is a proxy of economic loss. The very last couple of slides that I wanted to show you is an empirical application that we've introduced in Africa. We've used this machinery to design country-level insurance to insure loans of smallholder farmers that cannot access loans in Africa due to high weather variability and the very important riskiness of these smallholder farmers to weather impacts. So agriculture is at risk. Here I don't need to convince you. In the short term, you see higher and higher weather variability. This 0.5 here is the Russian heat wave and the blocking that caused Pakistani floods. That led to Arab Spring and so on, according now to some historians, food price spike and so on. In the short term, in the medium term, the yields of the main calories that we consume is going to decrease. And in the long run, there's full regions of the world that become unsuitable to grow certain key agricultural commodities. It has impact for businesses. So businesses, this is the 2013 heat wave in the US. Businesses, large businesses saw their shares value fall. This is a major crop trader. And in the long run, for those who like chocolate, the area suitable to grow cocoa is going to be cut by half in Ivory Coast. So this means that businesses and the economic system needs to, what we're proposing needs to change paradigm in how this market imperfection is addressed, and going through a thinking of shifting from a market failure thinking or rationale to sort of a framework where we are looking at how do we vertically integrate markets and share risk more efficiently amongst the different stakeholders that compose a value chain. I think I'm going to leave you on these slides. These are the sites where these farmers in Tanzania got access to loans because of that insurance mechanism that we put together, we introduced there. And these are some results of a randomized control trial that we have ongoing in Tanzania that show the type of farmers that we're working with and with whom we're going to see what this does. What this shows is that 88% of the farmers who got loans never previously had access loans, and therefore the transferring the risk of contract default to the markets helped to increase the credit worthiness of these farmers to weather volatility. So I'm going to leave you on that big question mark. That's what's going to happen in the future, because we have a randomized control trial that is ongoing and will provide further results in the next few years. So thank you, and sorry for the
Thanks, Erik. That was fascinating. Okay, questions, folks. Michael, your mic.
Thank you very much, Erik. Can you just say a few words about the expansion of the program from Tanzania to other countries in Africa and elsewhere that's underway?
Yeah. So we have another project that is starting pretty much now, that is bringing together these different disciplines: finance, climate, and here economic system is crop science, but there is going to be the energy system and so on. And we received support from the African Development Bank to expand this, what we introduced in Tanzania, in 3 other countries, in Uganda, Ghana, and Zimbabwe, which is leading us to on very interesting paths and confronting with my ignorance in many fields, many of those fields. So that's one of the challenges of this multidisciplinary research. Confronting yourself with your ignorance time after time, but it's quite interesting and quite challenging as well. Yep. So,
more questions, folks? Could you say anything about? I mean, this is fantastic, and it's fantastic to see that making a difference to smallholder farmers in Africa, but stepping back up to the bigger scale and the bigger picture, can you say anything yet about how you would see this approach altering the bigger picture damage function, or the knock-on implications of the results you're getting for the different way of constructing the damages? Do you see it could fundamentally change the kind of bigger global scale analyses? Or am I asking the wrong question?
Yeah, no, I sort of understand what you're asking here. Really, what has been introduced in Africa is really only the bottom part of this hidden Markov model, right? Then the objective that we have is to really have a robust characterization of these covariates, including how to make sure that that the covariates that we're choosing are properly chosen, that we are modeling their causality in a robust fashion, and also taking into account their dynamic behavior along the lines that you presented. This needs to be done in timescales that are compatible with investments and policy that are being designed right now. And if we link it to the financial industry, and here we're talking of insurance, but we would like to, how do you steer investments in different key sectors, optimizing for reduction in risk and transfer of risk, but that needs heftier investments. So here we are showing results in irrigation. Yeah. Irrigation will require quite hefty investments as a proportion of GDP, and so this will not be done with insurance, but rather with financial instruments of longer maturity, like bonds, where we are properly costing longer trends of climate. Yeah.
Well, that's a nice segue to tomorrow, I guess, and the finance focus.
Yeah. So would you like to go back to the slide that you had with the finance and the behavioral science part? You had 2 boxes. When Michael asked the question, you had some boxes with the finance and the behavioral science, this one.
That one?
So I suppose the finance, you were talking a little bit about bonds. This is what you have in your mind to include in your model?
Yeah, yeah. So when we have that diagram here is the reason to putting an arrow. I mean, I think here there should really be 2 arrows. The finance should be linked to the meteorology, but mostly with the climate. So both the low frequency and the high frequency. I mean, it's the high frequency, of course, that affects economic sectors, but that is driven by the low frequency. So here, this is a diagram that sort of materializes how should a bond be structured, and who should buy that bond. How is it going to modify the behaviors of different economic agents that are trying to manage their risk. So, I mean, here in behavioral science, we're in the context of Tanzania, we're working with a professor of psychology at Princeton who wrote a very nice book called the Scarcity, Why Having Less Means So Much. So what is the impact of scarcity on decision making, subject to different risks and so on. So yeah, this is kind of the research agenda that we're trying to push.
Thank you.
Okay, let's thank Erik and all the speakers from the session again.
Thank you.